Hi, good evening everyone. So I am Subhanu Haldar. So I am a PhD student at IIT Delhi. So we will be starting our sessions today for week 5. Then we will start. Yeah. So this is our topic today. So we'll be discussing about operating system fundamental week 5. So first is that we'll be starting from the very basics that so today our topic will be threads and you know that we proceed our class by solving some questions. So I will appreciate you if you try to solve this question by yourself, then I will make you understand. So I will give you a minute to solve it by yourself, then I will be solving it. Okay, fine. Okay. Okay, so let's start our discussion. So the correct answer of the question will be that is option D. Okay, so why? So the question is that which of the following statement about trade is or true? Okay, so threads can only be implemented in kernel process. No, we have already seen that threads cannot be implemented in the kernel process. It implemented in the user space. Then, so each thread it has its own file descriptor table for open files. So this is also false. All threads belongs to a process share or a common stack. So you can read out the options solution options from here. That thread can only be implemented in the kernel space. This is false, as we can implement thread in user space with the help of kernel threads. Okay. uh, so then second one is a process block has single file descriptor. All the threads belonging to the process share the same descriptor along with the data segment and heap code. So the second statement is also false. The third statement says that all the threads belongs to a process share a common stack. Okay. Sorry. All threads share a common memory address space but not the same stack. So I have drawn this image. So you can see here it share the data and heap. Okay. So memory address space but not the same stack. We augment multiple stack in the same address space belong to a process for each of the threads. This allow for parallel execution of the threads. Okay. Here you can see that I have added multiple stacks. Okay. Now since all the threads belong to the same process, results obtained by one of the thread might be used by another thread to continue with execution. So this is a critical section problem that this can be viewed as a critical section problem, that if a process of a thread is depending on the other output of the other threads, then there will be a critical section that who will finish first, then they will take the input from there. So hence by definition user level threads are not protected from one another, and job of maintaining protection is left to the developer. Okay, so threads belonging to a process are by default not protected from each other. Okay, so as a user you have to, as a developer you have to write your code such a way that this is protected from one another. Okay, so this is the next question, which is a multiple select question. Please see this and choose the right option. So as an overview, if we can if we can see that what are we doing to what are we intending to do. So first one is that we want to see what is multi-core programming. Okay, which is multi-core programming. Okay, now in second set we will be seeing what are the, so why do we need a multi-threaded kind of application. So multi-core, as there are multiple core, then we can create multiple thread. Sorry for my handwriting. Sorry for my handwriting. So as we have multiple core, we can do multi-threading also. So why do we why there is a need of multi-threading? So most modern application are multi-threaded. So thread run within application, multiple tasks with application can be implemented by separate threads like update display, fetch data, spell checking, answer a network request. So that's why we need a multi-threaded system. Fine. Now, process creation task with the application can be implemented by this kind of separate threads. Now, process creation is a heavyweight while thread creation is lightweight. Okay, so whenever you create a thread, yeah, so multi-thread models. So you have something called process and thread. Okay, so process is a heavyweight process and this is lightweight. Okay, so that's why it is easy to implement, and creation is very lightweight. So this can simplify code, increase the efficiency, and kernels are generally multi-threaded. Okay, so what does it mean by single-threaded process and multi-threaded process? So you have something like this. So here your code is present, your data is present, your files are present. Here you have some register. Okay, and now you have a stack. Now you have a one thread only. If this is a multi-thread, then what will happen? That you have code, data, files, and you have register. Here, as you have multiple threads, so you have multiple register, and you have multiple threads, so you have multiple stack. Okay, so this is the basic difference of multi-threaded applications and all. Now, which one or more of the following need to be saved on a context switch from one thread? Okay, so stack pointer need to be saved, program counter need to be set, and general purpose register need to be set, because you can see here that this register and stack. So this is stack pointer, program counter, and general purpose register is different from one of the stack. So there are page table based register. So you have page table, so you will be so you have page tables. So you have to remember then until which you have followed to load in the page table. Okay, so until which line of the code you have already running in your CPU. So this register holds the base address of the page table for the currently executing threads, and since all the threads of a process share the same page table, this register need not to be saved. Okay, because all the processes are saving using same page table. Okay, but the stack pointer, program counter, general purpose register, this is very unique to each thread. Okay, the register points to the top of the stack for currently executing thread. Since each thread has its own stack, the stack pointer needs to be saved and restored on a context switch. Ensure that the new thread uses the correct stack. Got it? Now, for program counter, this register contains the address of the next instruction to be executed by the currently executing thread. To resume execution of the new thread, the saved program counter needs to be loaded into the program counter register. Okay, and for general purpose register, this is a register. So this is used to store temporary data and intermediate result during the execution of a thread. Since the state of this register can be different for each thread, they need to be saved and restored on a context switch. Got it? So these are the explanation of this question. Okay, now come to this question. So we have a question for: consider each of the following multi-threaded code segmented in a mix C or pseudocode kind of language invoked by two process P1 and P2. So we have one process P1, one process P2. Each of the process spawns two thread T1 and T2. So spawns means it gives birth of two process T1 and T2. Okay, now, so this is the thing that create a thread to execute foo, create a thread to execute foo. Now wait for two threads to finish the execution. Okay, now my question is, which of the following statements are correct? That what the P1 and P2 will print. So this you need to predict. Okay, so please try it by yourself once, then we'll discuss about the answers. Okay. So what should be the answer in this case? So see that for P1 each process has its own address space. So you know that P1 has its own address space. So P1 has two threads, T11, T12 are created in main. You can see here it is the main function. So this is the main. Okay. In main function for P1, T1 and T2 is created. Okay. So we name it at T11 and T12 because for process P1 thread 1, process P2 thread 2. Both execute the foo function and thread don't wait for each other. Due to explicit locking mechanism, here mutual exclusion is there and hence no race condition inside the foo. Then y being thread local, both the kernels will print the value y as 1. Due to the wait in main, print x will happen only after both threads finish and x will become 2. So you can see here that whenever foo function is called, so this is your foo function. So this print statement need to wait because you will acquire a lock and you will release a lock. So this is a locking mechanism, or so there will be no mutual exclusion, you know. Okay. So because the developer has implemented the lock as a way that no thread will wait for anyone. Okay. So they can execute without no race condition inside it. Okay. So there will be no race condition. So this if this T11 and T12, if when it will be in foo function, then as there is acquiring lock and releasing lock option is there, so there will be a mutual exclusion and between T11 and T12. Okay. So the x and the value of x will not be overwritten by T12 when T11 is reading it. Okay, so that should not be the case because of the locking mechanism here. So that's why the answer is both P1 and P2 will print value of x as 2 because there is a locking mechanism and it is mutual exclusion. And both T1 and T2 in both process will print a value of y as 1. Okay. Same thing happens here as P1 so for P2 we create a thread T21 and T22. So for T as we created T11 and 12, here we create T21 and 22. So so the correct answer is A and D. Got it? So suppose weight is removed from the main, then possible x values can be 0, 1, 2 because there is no locking mechanism. So as there is locking mechanism, that's why this will be run in mutual exclusion. Got it? So this is the next question, that which of the following is shared by all threads in a process. So you have to give the correct answer. So we know that so this is an important information for all, that for pre-process items this is shared by all the threads and private for each of the thread. So this is a very important information, that for pre-process item, address space, global variables, open files, child process, pending alarm, signals and signal handler, accounting information, this is shared in pre-thread system. But what is per thread? This is called per process system, and one is per process system and one is per thread system. So first column lists this first column lists some item that shared by all threads in a process. The second one lists some items that private to each thread. So what are the important one? That program counter, register, stack and program state. These are the private for each of the thread. This is private for each of the thread. Got it? Okay. Okay, fine. So this is the answer of this. So what will be the right answer of this question? So the right answer will be option B, which is 3. That address space is only shared by all thread in a process. Okay. Then program counter, stack, register, these are not, this is private for each stack. Okay. Now can you answer this question? Okay, so what will be the answer for this? So the answer is that a thread shares with other thread a process to which belongs to. It thread with code section, data section. In data section we have two options: static plus heap, address space, permissions, and other resources, as for example files. Okay, therefore D is the correct answer, that both heap and global variables. Got it? So here you can see a lot of question on this threads and all. So you can see this question is repeated. Yeah. So now our question is, which one of the following is false? You can see that this is false, not true. Okay. So is it user level thread are not scheduled by the kernel? When a user level thread is blocked, all other thread of its process are also blocked. Context switching between user level thread is faster than the context switching between kernel level thread. Kernel level threads cannot share the code segment. So which one statement is false? So you can see in the solution that statement D is the true one. Okay, so this is a false statement. This is true, this is true, this is true. Okay, so because thread can share the code segment, they have only separate register and stack. We have drawn so many pictures of this. Okay, that yeah, so this one we have already done so many picture of this one, that in thread we have a process like this. Yeah, so this is so we have stack register. So these are multiple threads, these are threads. Now here code and data is same. Okay, so in user level threads are scheduled by the thread library and kernel knows nothing about it. So A is true. So what A statement A is said, that user level threads are not scheduled by the kernel, but user level threads are scheduled by the kernel, because you can see that user level threads are scheduled by the thread library and kernel knows nothing about it. Okay, so this is true. When a user level thread is blocked, all other threads of its process are also blocked. So B is true. With a multi-threaded kernel, user level thread can make non-blocking system call without getting blocked. But in this option, it is explicitly said that thread is blocked. Okay, you can see the question, that when a user level thread is blocked, all other thread of its process are blocked. But when a user level thread is blocked, all other threads of his process are blocked. So B is true with a multi-threaded kernel, because the multi-threaded in a multi-threaded kernel, this multi-level threading can make non-blocking system calls without getting blocked. But so this is the situation. And last option is context switching between user level thread is faster, as they actually have no context switch. Nothing is saved in the restored. Nothing is saved and restored while for kernel level thread. Register PC and the program counter must be saved and restored. So C is true. Okay. And next question is that a thread is usually defined as a lightweight process because of an operating system maintains smaller data structure for a thread than a process. In relation to this, which of the following statement is true? Okay, now we'll see which one is true. That one per thread basis, OS means operating system, maintains only CPU register state. CPU, this is not maintain only CPU register. This maintains CPU register, but along with that, it also maintains stack. The operating system does not maintain a separate stack for each thread. On per thread basis, the operating system maintains only scheduling and accounting information. Okay, so we'll see the overview. Many of you would not agree at first that that operating system on per thread basis maintains only two things: CPU register and stack space. Okay, It does not maintain anything else for individual thread. Code segment and global variables are shared. Even the TLB means, what is TLB? TLB is translation look aside buffer. Okay. So TLB and page table are also shared since they belong to same process. So option A would have been only correct if only word were not there. Okay. It is second statement is absolutely false, and its third statement is true, as it says operating system does not maintain virtual memory state for individual thread, which is true. Okay. Now the question is like this, that let the time taken to switch from user model to kernel mode execution of T1, while time taken to switch between two user process, okay, be T2. So which of the following is correct? So this is the question. Yeah, you can solve the question by yourself. Okay, so what will be the answer? So time taken to switch to process is very large as compared to time taken to switch between kernel and user mode of execution, because when you switch process you have to do a context switch. So save the PCB of the previous process, note the PCB of a previous process in Linux user has over, so has over 95 entries. So you can save PCB of previous process of 90 as much as 95 entries. Okay, then save the registers and then load the PCB of new process and load its register. When you switch between kernel and user mode of execution, operating system has to just change a single bit at hardware level, which is very fast operation. So option C is correct, T1 less than T2, because in T1 switch from user mode to kernel mode is a one hardware bit operation, but switch between two process, that is T2, that is you have to do some changes with PCB, register and program counter. Okay, so that's why T1 is much faster than T2. Okay, so can you solve this question by yourself? Okay, so in this question, that consider the following statement about user level threads and kernel level threads. Which one of the following statement is false? So context switch time is longer for kernel level thread than for a user level thread. Yes, context switch time is longer for kernel level thread than for user level thread. This is true as kernel level threads are managed by the operating system, and kernel maintains a lot of data structure. There are many overheads invoked in kernel level thread management which are not present in the user level thread management. So that's why this statement is true. Now, user level threads do not need any hardware support. So this is very false. So user level thread do not need. This statement is true. Actually, this is true because as user level, the threads are implemented by libraries programmably. Kernel does not seize them. Related kernel level thread can be scheduled on different process in multiprocessor system, and this is true. Blocking one kernel level thread blocks all other related threads. This is false because it happened user level thread. This would be true. If this is for the user level thread, this would be the true. So this is the actual false statement. Okay, option D. Now the question is that which one of the following is not shared by the thread of the same process? So stack, address space, file descriptor table, or message queue. So which one do you think? So the two. So we are doing this same question from from our beginning only, that we know that the stack is not shared. Otherwise, address space, file descriptor table, and message queue, these all are shared for the by the threads of a same process. Okay. Now, so now we will be starting our main question for the yeah. So this is the question, that consider the following statement with respect to user level threads and kernel supported thread. So which one of this is true? So context switch is faster. Context switch is faster with kernel support thread, and so this is a false statement for you, because you can see I have written it here that user level thread switching is faster than the kernel level thread switching. Okay, so for user level thread, system call can be blocked the entire process. So this is a true statement. Kernel supported by threads can be scheduled independently. Yes. User level threads are transparent to the kernel. Yes. So 1, 2, 3 and 4 are the true statement. 1 is the false statement. Okay. Now choose the following correct option here. So the question is about that MS, which is the correct option. So MS-DOS operating system supports a single thread. Java run. So this is true. Java runtime environment supports one process with multiple threads. This is also true. Windows operating system support multiple thread per process. This is also true. This is a remember based question that you have to remember and you have to answer. Solaris operating system support multiple thread per process. This is true, and so all of the above is true. Fine. Which of the following operating system support kernel thread? Okay. Windows, Solaris, Linux, Mac OS, which one? So all of the above is true. Yeah. So this is an important question, that which statement is incorrect which statement is incorrect to a many to one trading model. Okay. So you know that what are the many to one trading model. So in trading, so we have many to one, one to one, and many to one, many to many, and one to one. Okay, and why this came into the picture? That So this is the relationship between the user and kernel thread. Okay, so three common ways of establishing relationship between the user level thread and kernel level thread is this one. Okay, so in many to one model, many user level thread map to a single kernel thread, and one thread blocking causes all to block. So this is not a good option. So Solaris green threads, GNU is GNU portable threads. These are options of Solaris and GNU portable. Solaris green thread and GNU portable threads are the option of many to one model. Okay, so in many to one model, multiple threads may not run in parallel on multi-core system because only one may be kernel at a time, maybe in kernel at a time. A few systems currently use this model, and in many to many model allows many user level thread to be mapped to many kernel thread, allows the operating system to create a sufficient number of kernel thread. Solaris prior to version 9 are this kind of threads. In two-level modeling, we have IRIX, HPUX, 264 Unix, Solaris 8 and earlier version as many two-level modeling. Like two-level modeling is like you have user thread and you have kernel thread. So these are the threads like this. These are the threads, and this is modeled as like this. Okay, user thread and kernel thread. Okay. Now, in thread libraries provides programmer with API for creating and managing thread. Two primary ways of implementing it: library entirely in user space, kernel library supported by the operating system. Three primary thread libraries are POSIX, pthread, Windows thread, and Java thread. So of this, you already got some questions. So this is the next question. Can you please solve it? So you can see that which one is the true option among these. Okay, so each user thread maps to a kernel thread. Yeah, this is also true. Multiple threads can run in parallel on a multi-core system. This is true. The process will not be blocked even if a user thread executes a blocking system. Well, this is true. It needs full support from the operating system to create and schedule threads. Okay, this is also true. Okay, so this none of the above is the true one. Now in this question they are asking that which statement is incorrect in many to many threading models. Okay, a user can create many user thread. This is false. This is true that a user can create many user thread. So user can do anything. depending on the system architecture, the kernel creates a limited number of kernel threads. This is also actually a true statement, but we need the incorrect one here. The process will be blocked if a user thread executes a blocking system call. The multiple threads can run in parallel on a multi-core system. It needs full support from operating system to create and schedule threads. Okay. So this is the only false statement here. Multiple thread can run in parallel on a multi-core system. Because in multi-core system, the process will be blocked if a user thread execute a blocking system call. So this statement, that's why, is not correct. Got it? Now try to solve this one. Okay, so you know the answer, that is all of the above. Now for this question, next question, what will be the correct answer? A signal. What is a signal? So signal is asynchronous event. Yes, this is true. Is handled by the appropriate signal handler. This is true. C is delivered by to process when a interrupt occurs, and D can be sent to a process by another process. Okay, so all of the above is true. Okay. Now the next question is, in a multi-threaded process, a signal can be delivered to. Uh, this is also all of the above are correct. That in a multi-threaded process, a signal can be delivered to the thread to which signal applies, which where the every thread in the process see certain threads in the process, a specific thread to receive all signal for the process, and that's why all of the above is correct. Okay. Next question is about the p-thread call, p-thread create system call. So in p-thread system call, it returns the thread id if the thread id if the thread id creation is successful. Okay, so you know that in thread also returns something. Thread always returns something 0, 1 or positive value. So here pthread returns the thread id if the thread creation is successful. Okay, now this pthread returns an error number if the thread creation is unsuccessful. In C, option C, this pthread create fails if the system lacks the necessary resources to create a new thread. This all are true. So this is kind of information only. So in pthread, what is pthread create system call is fork. Okay, so like fork has positive 0 negative, then pthread returns something. So pthread system call is used to create a new thread. So this all, of course, create function call is there, so that's why you have to, because so that's why this is used in creating a new thread. Okay, now that's why all of the above are correct. Now this is a beautiful question, that for a single thread kernel, that is single thread kernel. Okay, so this is a kernel, only there is only one thread. Okay, so number of system call that can be handled by the operating system concurrently is at most once. Okay, why at most one? Because we have a single thread. If this is there is two thread, multiple threads are there, then the option would be different. Okay, now we have arrived in the next chapter, where we will be solving the problem of our fast come fast serve policies, and we have FCFS, where we will be determining the average of it, and like this. Okay, so we will be looking into the implementation of here. Okay, so why this is important, what are the important parameter of a process? So we have seen that arrival time. So time when a process arrives in a ready queue, so this is called the arrival time, or in short we say we denote it by AT. Now we have burst time or the execution time, we denote it by CT, and we have completion time, we denote it by CT. Okay, so we have AT, BT, CT, right? Now, so we know that in a process, from the state of a process, it can go to wait state to dead state, or wait state to bus state. So we know that it can go to ready to run and run to terminate. So how we calculate the CT minus AT? So we calculate CT minus AT is equal to BT plus WT. So we denote turnaround time by CT minus AT and waiting time by TAT minus BT. So what is the response time? Response time is when a process is processed for the first time after waiting a long time. So in CPU scheduling, you know that who is responsible for scheduling the CPU? So short time scheduler initiate this CPU scheduling. Where it initiates? It initiates in the ready state. Okay, you can see it here. Okay. Now it goes to the running state. Okay. So when it schedule it, so when a process moves from running to terminate, running to wait, running to ready, so or new to ready and wait to ready. So I have marked it 1, 2, 3 like, because these three are starting from running. This is going from running to terminate, running to wait, and running to ready. And this one is new to ready and wait to ready. Got it? So that's why. So this is, you all know these are process state of the process. From a new it can goes to ready, from ready it can either run, or from run it can go to ready. From a waiting process, when it finishes its running, it can either terminate or it can come to wait state. From wait it can go to ready. Okay. So in first come first serve, we will be given with AT, BT, CT, like arrival time, burst time, and completion time. For each of the process will be given. So how will I execute the process? So so this is this chart. This chart is called Gantt chart. Okay. So we will design a Gantt chart based on this. So we have the arrival time here. So we will look into the arrival time. So 0 is the arrival time. So we start from 0, then 1, 2, 3, 4. So you can see that each time instance one process has arrived. So how we will manage the process? We will. So if all are in the ready state, then which process will run first? The process which came first. So we can see from the arrival time that process 1 came first, then process 2, then process 3, process 4, process 5. Then we can look into the burst time. So burst time is basically it will be given that how much time it required to process in the CPU. So then we can calculate the completion, the CT. We know the CT. Okay. So by from this Gantt chart. Okay. So from 0 to 4 process 1 ran. From P2 ran from 4 to 7 because the burst time is 3. For P4 burst time is 1, so that's why 7 to 8. Now burst time is here burst time is 2, so that's why 8 to 10, and here burst time is 5. So how we calculate CT? We calculate CT by TAT minus BT, and we TAT by CT. You can see this formula. TAT by CT minus AT and waiting time by TAT minus BT. Got it? So this is the formula. TAT by CT minus AT and waiting time by TAT minus BT. Okay. So how we calculate the average waiting time? We have the waiting time. We sum it up. Okay. And we divide it by number. So this 5 is the number of process. Okay. So this is how we calculate the average waiting time and average turnaround time. Okay. Now this is implemented by a queue data structure. Time complexity of this is number of process. Okay. So this is how now if we have the option of preemption. that you know that there are two types of processes that can come, that with preemption and without preemption. So if we have a process with preemption, with where delta, that preemption time is 1 unit of time, that is the context switching time. Okay, then what should we do? So first we have a context switching time here, then we'll run p1, then we'll have some context switching time after each process. That means that after each process there will be a context switching time. So that's why everywhere here I have added a delta, which is the context switching time after each of the process. Okay, then I calculate my TAT is equal to CT minus AT, and WT is equal to TAT minus BT. So this is the formula by which I calculate this TAT, and by which I calculate this waiting time. Okay, now come to our question, that can you please try to solve this question? This one is the first question. Yeah, this question was the first one. Can you please try to solve it once by yourself? So what we have learned from here, that yes, so we can see that P1 is coming at first, so we have written P1 here, and the bus time is 11, so it is running from 0 to 11. Then P2 is coming, it is coming at time 2, but has to wait because P1 is running, so that's why P1 is running until 4 it will run for 4 time unit, so 11 to 15. Then P3 has already arrived at timestamp 3, but he has to wait until all are finishes. Then P3 is running from 15 to 17. Then I calculate CT. CT is T8. I calculate CT from here, which is 0, 11, 15, 17. 11, 15, 17. Okay, now how I calculate TAT? TAT is CT minus AT, and WT waiting time is TAT minus BT, and that's how I calculate the average waiting time, which is 7. Okay, so this is the correct answer. Now what should be the case for the same thing? So the all are same, but I have to determine the average turnaround time from this process only. So average turnaround time, I can see that this is 38. So, summation of this all is 38. So average turnaround time is 38 by 3. Okay, so which comes into 38 by 3, which is 12.66. Okay, fine. So yeah, so this is the correct answer. Okay, now we have the same thing, but we need to find out the average response time. So average response time, how should I find out response time? So this is the response time. Okay, response time of P1 is 0, response time of P2 is 11, response time of P3 is 15. So I add it 0, 11, 15 by 3, and I got 26 by 3. So what is 26 by 3? So this is 7. Okay, now the question is, which statement is true for preemptive scheduling algorithm? So I have told you that one is preemptive scheduling algorithm and one is non-preemptive scheduling algorithm. So there are 4 options. The CPU is allocated for the entire burst time of a process. This is false. Race condition will never occur if data are shared among the multiple processes. Okay, so race condition can occur in this system also, and Unix OS is not supporting preemptive scheduling. Unix OS support preemptive scheduling. Round robin is not supporting preemptive scheduling. Round robin is a best example. So we'll see the round robin algorithm in next week. So round robin always use the preemptive scheduling. So a low priority process will wait a high priority process arrives simultaneously. So this is the correct answer. Okay. Now so now the last question is this one. Okay, so what is the answer? So answer is all of the above, because the selection of process scheduling policy affects maximum CPU utilization, maximum throughput, minimum turnaround time, and minimum response time. Okay, it affects all. Okay, so this is all from my side for today's lecture. Okay, so we will meet on next week again. Okay, so thank you everyone for joining the lecture. Okay, thanks a lot.